Thank you for giving me the opportunity to come and talk. I'm actually a little bit awkward, a little bit concerned that I'm going to tell you things that you're going to tell me are wrong, because I feel like there are certainly people in this room that know more than I do about this, so it'll be interesting to see how perceptions differ. I guess that's one of the things that I've learned. I actually gave this talk about 2 weeks ago in Barcelona and found out that a number of the things that I took for certain people in Barcelona said, no, in Europe we don't think that's true at all. We think that this is true. And so it was kind of interesting. So I'm curious to see how some of this appears here. What I want to do is to try to convince you that clouds are useful for science, and that depending on what we mean by clouds and what we mean by applications in science, there are kind of good matches and bad matches. Also to talk about two specific applications, finite difference time domain electromagnetics, which is what I did my PhD on at Northwestern, and montage, which is an astronomic image mosaicing application that I've worked on at JPL. And hopefully through that to think about what the important features of clouds are and how they map to applications. And so just to start off, this nice NIST definition. A cloud is a computing capability that provides an abstraction between the computing resource and its underlying technical architecture, enabling access to a shared pool of configurable computing resources that can be rapidly provisioned and released, minimal management and service provider interaction. So I'm going to go through kind of a bunch of stuff here. Please feel free to ask questions when they come up. If I say something that you don't think is right, let me know. We can talk about it at that point. At the Grid 2009 conference last fall, Rich Wolski gave a talk on the work that he was doing on clouds and came up with this assertion about the differences between clouds and grids that I thought was interesting. And so Rich's point was that clouds have a situation where individual users only get a small fraction of the overall resources, whereas grids, individual users can get a large fraction of the resources, if not all of the resources in some cases. Clouds in general don't have a support for federating different clouds, except at the client level, and grids are really completely about federation and putting resources together at the system level. Clouds in theory are opaque with respect to resources, and grids often try to expose the resources so that you can optimize for specific resources. So based on that, Rich talked about different architectures for each and then went on to talk about eucalyptus as the cloud architecture, which I'm not going to talk about. But it's worth mentioning that this is, in my opinion, this is the US view. And the European view is much more fuzzy. And I don't think that these definitions would be agreed to at all. Maybe the federation part, but anyhow. So I'll go on and I'll talk about some more of these things as we go. So clouds, probably most people have seen this before. We've got kind of this three-layer idea of looking at capabilities of clouds, of infrastructure as a service, platform as a service, and software as a service. And depending on where you come into this, you get different advantages and different disadvantages as well. And there are, on the left side, there are examples of these three different levels that exist in commercial worlds today and public worlds today. And then on the right side are kind of some of the technologies or things that you can do in terms of private clouds that match those layers as well. So with that brief introduction, then I'm going to talk about the two different applications, and then we'll come back to clouds and talk about how things fit together and what we've learned. So the first thing is electromagnetics, finite difference time domain. My experience in this was when we were moving from sequential programming to parallel programming. And so I wanted to talk about that change to some extent in the context of electromagnetics. So we start with Maxwell's equations, of which there are a number of versions. We pick a version that matches the problem. And here I'm going to try to talk about radar cross-section as an example problem a little bit. So we have an object that we model in space. We have some incident wave that comes in and hits the object and interacts with the object. And then we have some scattered wave that comes back that we measure. And so just as an example of this, where we don't necessarily have the scattering, we've got a dielectric lens that looks like this, roughly a fourth, a little bit more than a fourth, that we set on top of a material, and this is a cut through the material where this is the top. And so we're seeing that we're getting some focusing here of the energy from this lens, which is what we want. The point of this is really to show that this technique, finite difference time domain electromagnetics, works. It's useful for problems. Here we have the case where we've got some incident wave coming in from the top, and we can understand exactly how that interacts with the object. We don't care about scattering in this case, but in a lot of problems we do. I'll provide the slides to whoever actually wants them. I'm not sure if there's a mechanism for doing that or not, but hopefully there will be. There will be a few equations here that I'm not going to talk about in detail, but I just wanted to put them here in case somebody wants to look afterwards. But effectively we're starting with curl equations, where we've got 4 variables, 2 electric field, 2 magnetic field. We pick a specific set of media that lets us go down to 2 variables. And when we combine these, then we get the equations on the top, which are the electric and magnetic fields, where the magnetic field H is dependent on the electric field E, and vice versa. And if you write these out in vector terms, the vector components, you get these 6 equations. And the thing that actually was the most amazing to me when I was in grad school, or actually when I was an undergrad, is that this guy Kane Yi in 1966 looked at these equations and came up with this geometry and said, you know, if you use this geometry, all the equations naturally fall onto the geometry, and everything becomes very easy to solve, and we can do computer implementations. And I don't know exactly where this came from, but it's interesting. So if you look at the top left equation, the dx dt, that's this hx component, and it's equal to a partial derivative of ey in the z direction, and z in the y direction. So it's basically a loop around this side of the cube. So in a computer, you can do this pretty easily. You can write down these equations, all 6 of them, and you can solve them. And if we simplify things to 1 dimension, just to make this a little bit easier, we just take 2 of the equations that are consistent with some simplification. We do second order differencing, central differencing in time and in space. So we get something here that's a time difference. So we've got superscripts here that are time steps, q plus a half, q minus a half. Then we've got a spatial difference over here that's a time step q. So basically we've got something in the future based on something in the past and something in the present. So that's good for time marching. So we can go ahead and do this pretty easily. And if we're going to be doing time marching, we have to figure out how the spatial step and the time step vary, and so there's a Courant condition that people use. But effectively, you can think of it that energy shouldn't propagate more than 1 spatial step and a temporal step. So in 1 time step, energy can in theory move 1 space step. And so this is actually what a 1D grid looks like, where we've got EZ components and HY components alternating. Because they're at half spatial steps and half time steps, this gets a little bit confusing. So we just pick integer indices to program this. This is actually one of the things when the Chapel language was coming out of Cray. I was actually very excited because at one point it was going to have arbitrary indices, so we could have halves in there, which I thought would make this much easier to explain and to teach, but I'm not sure that that's happened officially. So we pick integer indices. And so what we do in a 1D code is we define some parameters of the media, of the material that we're using, initialize all the fields to 0, then loop over time, so do time stepping. And within the time stepping loop, we have an alternating space loop over the electric fields and a space loop over the magnetic fields. And so this is time step n plus a half, n plus 1, n plus 1 and a half, and we keep going off into the future until things settle down or we get to a steady state, or all the energy is gone, or whatever the final condition is that we're looking at. So there's complications, of course. So we have issues that this field is basically related to these 2 fields half a time step earlier, and this one's related to these 2 half a time step earlier. So what do we do with this one? All right, we've got boundary conditions to worry about. If we have this relationship that basically energy is moving 1 spatial step per time step, then we know that what's here is what was here 1 time step earlier, and we can actually just substitute and and do that. If we don't have that, we're in 2 dimensions, 3 dimensions, something more complicated, then things get a little trickier. And there's, in electromagnetics anyhow, the Muir radiation boundary condition from 81 was kind of the standard thing when I was starting this for quite a while. And then a guy in France, Berenger, came up with the Berenger perfectly matched layer condition, which is kind of interesting and isn't worth going into. It's much more complicated, but it's much more accurate, and that's what people use today. There's also questions about how we get energy into the system. So before I mentioned that we have incident waves and we're looking at scattered waves. So we have a principle of superposition, which says the total field is the incident field plus the scattered field, and we can apply that anywhere. So what we do is to use something called a total field scattered field formulation, where we've got something in the main part of our grid that we call the total field and something in a boundary layer that we call the scattered field. And we can compute pretty simple equations to match those, and those equations have the effect of putting the incident energy in as they're taking the scattered field, as they're taking the incident field out as well. So basically we're doing adding and subtracting along a 2D locus, if you think of this in a 2D rectangle on a 2D grid or a 3D volume on a 3D grid, but along just on the surface. Okay, and then and so this is basically what that actually looks like, just as an equation on a 1D grid. So it's a very simple equation in 1D, more complex in 2D or 3D. The other thing is that if you're looking for radar cross-section or scattering, at some point you can look at the energy here, and that's what the energy actually is at this point, the near field energy, but you really want to know what the far field energy is. And so effectively you can take the energy here and look at a Green's function to figure out what's going on far away. In 2D or 3D, you have to sum up a lot of Green's fields, again, around a surface in order to do that, Green's functions around a surface. But again, it's just a complex thing. It's not hard to do. It's just bookkeeping to get it right. Okay, so this is what people were doing. Well, that doesn't look good at all. There's a cabinet on that side with a computer in it, which you can't really see at all, which is interesting. I don't know, not sure what to do about it. Anyhow, so this is we've got a rack here that's about this tall. That's a 32-node Intel 286 Hypercube that was an IPSC D5. We didn't have that much money. We had a D4, which was a 16-node system at that time. So this is 1987 roughly. Distributed memory, right? Lots of different nodes. They're really little 286 computers, which are IBM PC XT computers, I guess, at that time. And they used iSend and iReceive calls to communicate data from one node to another. The code that I was using, which had come from my advisor and lots of other graduate students, as is traditional, had been previously vectorized, and we'd also done a little bit of work with shared memory parallelism as well. So there were a couple of things that had been done, and we kind of knew what the code was. But going onto this 2D, into this parallel domain of distributed memory, right, we had to worry about ghost cells. So this is common now. It was kind of interesting when we first thought about it. So we've got, we've got these cells that belong to our processor, but we can do the update of this one with these, but we can't do the update of this one because we don't have the cell that goes over there. Right, so we communicate the cells on the boundaries from the neighboring processors. Right, so this is quite standard today. Again, interesting at the time. We worry about load balancing as well. So as a sample domain where we need 4 processors, we need to worry about balancing the memory, balancing the work, balancing the communication. Right, effectively, if we do all of those well, then we get something that's load balanced. We can balance the memory just by dividing things up into 4 subdomains. I don't know how to draw this well, unfortunately. I keep trying and don't succeed. So these are the boundary cells that are coming from this processor to go to this processor. All right, so the boundary cells that are being computed aren't even. The 2 processors in the middle are doing more sending and receiving than the ones on the end. If we go on and talk about the boundary conditions themselves, all the cells on the end have much more work to do than the cells in the middle. We've got these other things, the total field scattered field formulation. There's a boundary there. There's a boundary for the far field. So actually getting this right in practice is extremely painful. We do it by hand. We did it by hand in 1987. We don't have any better way to do it today. This is one of those problems, I guess, that I would say is not interesting in computer science, so people don't do it, but it's interesting. So it ends up that people usually do this by hand, is my experience. Okay, sorry, and this is just looking at those different cells. But anyhow, the point of this is that this works. People do it in practice all the time now. This is just, again, another sample problem. So this is this is the problem domain that's being solved. The dotted lines are the domains where we're doing decomposition. We put in periodic boundary conditions on this side, on the front and the back, and absorbing boundary conditions on the bottom and the top. And then we can have a wave that comes down, and we can look at this, and we can observe plasmon behavior that we would want. We do this to design physics circuits, electrical circuits, optical circuits. So this works fine. Looking at speed up from a few years ago, you can see that we're going out to a big number of processors, 384 processors, roughly 400 processors. We get pretty good speed up. We can parallelize this reasonably well. We can do the load balancing. Okay. So in kind of a fast journey, what I hope I've talked about is that finite difference time domain really is a set of loops over a set of components within a time-stepping loop. We have a usage model, in this case, where we set up a simulation, we run it, and then we look at the output data. So we do this once, we come back a week later, 2 weeks later, and do another problem. It's a simple idea. The way to do this was thought of in 1966, so it's relatively old, but it's complex to code it, and there aren't really good tools in general that make it easier, so it's still painful today. We have a fixed size physical domain, and because we're using domain decomposition, we get a static mapping to a fixed size set of processors that we're working on. It's a tightly coupled code. It has alternating computation and communication steps. As I said, load balancing is complex in practice. This uses MPI now and is common. So this is intended as an example of a transition that worked, that happens. Right? We went from sequential to parallel for problems like this where we can use domain decomposition. This is very common and happens in lots and lots of fields today. Okay. Let me go on then to the second example, the astronomy application of montage. Here we started with basically what was a parallel application and went to a grid. So montage is an astronomic image mosaicing service that's part of the National Virtual Observatory project. There's a website that you can get more information on it if you're interested. I was part of the team at JPL that did some of the work. There was another group at Caltech that did a lot of the astronomy-specific pieces. And then we had a group at ISI at University of Southern California that did the grid piece. And just names of different people that were associated. So what montage does is it delivers custom science-grade image mosaics. So we start off with a set of pictures, a set of telescope images. We combine them together into a single image that has the resolution of each of the individual images, but has the overall field of the overall object that we're looking at on the sky. Montage basically allows the user to say, here are the images I want, here's the output that I want, and it does everything for you after that. It does the reprojection, given the projection, the coordinates, the sampling, the size, and the rotation. Montage was designed specifically to preserve astrometry and flux very accurately, because this is what astronomers wanted. There was a previous version of this that was very nice from a computer science point of view and very fast. But then it turned out that nobody wanted it because we hadn't done the science well enough, even though the computer science was fine. So this one we focused on the science first and the computer science second, I think. Yeah, so astrometry is basically the position of the energy, and flux is the amount of the energy. So effectively, if you think of the energy basically as being the CCD over some time, read some amount of energy coming into a pixel. This basically just means that we preserve that amount of energy very accurately, as well as the positions. So, let's see. And so montage, when we designed this, we realized that people would want to do different things with it at different cases. So it's a bunch of different engines that do different things, and each engine is an executable. And so that allows us to do different scripting or other things around them to combine them in a way that, that works better. I'll talk about that in a minute, a couple of slides. The reason that montage or something like this is interesting is that a lot of structures in the sky are larger than the individual images taken from a telescope. When you're looking at faint sources, you may have very low signal to noise, and you can stack images that have low signal to noise, and the signal combines and the noise doesn't. So you can do montaging for that purpose. You can also look at multi-wavelength image federation, where you're looking at different telescopes at different times that took images of the same object, trying to understand how those all go together. And this is going to be a bad picture, I'm pretty sure, as well. Yeah. Sorry, this projector is not too exciting for the minute. But it seems like the tradition is if you're showing something with astronomy images, you should show nice pictures, which I'm trying to do, but failing. Okay, so montage has had 3 different versions up to this point. We had an initial version that emphasized accuracy. Did everything sequentially on a single processor, but did it very well and was very well tested. A second version where we improved the performance of the code overall in terms of the speed and the use of memory. We added MPI to enable it to run in parallel, and then we added grid tools to enable it to run on TeraGrid or on other grids. And then there's a third version that basically adds utilities and bug fixes, but doesn't really change much of the underlying architecture. And anybody can get this if they wanted to try it. So let me walk through what montage actually does, because this will hopefully make more sense. We start off with 3 different images in this case that were taken at different times, so they have different sky that they've gone through and they're shaded to indicate that. The user says what they're interested in as an output, and that's probably a different projection. And so we reproject the 3 images into a different projection. We then look at the differences between pairs of images. We fit planes to those different images, different regions, which gives us equations. We put the equations together into a set of equations. We solve the set of equations. We apply that then to the images that we have. And then finally, we co-add the images into one mosaic or multiple tiles of a mosaic, depending on what the user wants. So let's see, to talk about a few different things. So each of these, basically, this is a C executable that's running on an input image and creating an output image. All of these, right, red ovals are C executables. You can see that we've got parallelism at a few different levels here. Right, so we can run all of these at the same time in parallel, as far out as they go. So this is a pretty simple example with 3. Obviously, we can go to tens of thousands, hundreds of thousands. So we can do more work than we have processors in a lot of cases. There's also dependencies that are implicit. So if we've done this job and this job, and we have these 2 output files, we can then do this job next. Right? We don't have to wait until this one. Right? So we can do things in arbitrary orders. So effectively, what we ended up doing with this was to express this in 2 different ways. One was that we took all of these levels, if we want to call them that, levels in a workflow, and put them into MPI jobs. So we have an MPI job that basically uses a lot of processors and does a round-robin assignment of all of these things and takes an input directory and looks at all the files in the input directory and builds an output directory. And we've got kind of a bunch of those, and then we write a script that calls all of those MPI jobs in sequence, which works fine. We also then look at each of these jobs and say, this is an executable. It has an input and an output. This executable is dependent on this input and this output, or sorry, this input and gives you this output. So we describe all this basically as a directed acyclic graph for a DAG, and then we use tools that work on DAGs to actually run this across a grid. So I think that's what I'm going to say here. Where I was saying at the beginning that the kind of cloud and grid are fuzzy terms, grid in particular has been a fuzzier term over time, and has meant a lot of different things to a lot of different people. So what we wanted to do at the time of montage was to do something that was as general as possible. And so, as I was mentioning, we described the flow of data and processing as a DAG. and then we use grid tools to execute that DAG, first to map it onto some specific resources and then to actually run it. And we built an architecture that puts all of this behind a web portal that lets a user do all this without actually seeing it. So this is an example DAG. This is a slightly larger one, so now we have 10 input files. So this is data being staged in from catalog somewhere. This is the projection, the differencing, fitting the planes, creating an equation, solving the equation, applying those solutions, doing the co-addition, and then staging out the data onto a catalog somewhere else so that the user can get it at the end. Once we have this, then what we do in the grid version of this is we use Pegasus from ISI to take this abstract definition that doesn't say anything about resources to look at grid information systems and actually figure out how to map this onto resources, and then to give it to Condor DAGman to actually run on the resources somewhere using my proxy to make sure we do the accounting right and get the user right and stuff like that. So that's the grid version. Going back to the MPI version, which I talked about, but I don't really have a slide about, this is effectively just a graph where we're looking at the different stages that happen in the script. So this is anything with an exec is an MPI. So this is an MPI job. This is. There's some other jobs here that are looking at directories and trying to build up, basically build the number of files that are in the directory so that the MPI thing knows what to deal with. And we have time going across, and you can see that we go through all these stages from starting with what do we have at the beginning to doing addition at the end. This is a 6 by 6 degree mosaic on 64 teragrid processors on Mercury, I think, at NCSA. And it takes about 27 minutes to run. All right, so this works fine. We do the grid version, and things are a bit different. Let's see, so what's a bit different? So we start off with something called MDAG. So this is the thing that actually builds the DAG from the input, which we didn't have to do in the MPI case. We could just look at the input files. We've got Pegasus doing actually the mapping of the abstract DAG onto the concrete DAG. And then we've got a bunch of actual tasks that happen. Because, again, these tasks don't happen quite stage by stage, there can be some overlaps. It's a little bit hard to figure out exactly how to draw this in an easy way. There are some weird things that happen. We get some areas where it looks like nothing's happening. Some of that is a consequence of not being able to time things really very well, again, because we've got different stages happening at the same time. Some of that is because we've got this thing, Condor DAGman, that's actually taking the output of Pegasus and running it. And it does polling, basically, to look at when a job is finished and when it should launch a new job. And so you can run into situations where it actually misses a few cycles, even though it shouldn't. But overall, let's see, this is it's the same problem, same computing system. We're out around 30 minutes, so it's roughly the same amount of time as well. So let's see, is there anything here that I haven't said already? Okay, so there's queuing delays in both cases here. I've ignored them because in the MPI case, we wait for a queue to run. Then we run all the MPI jobs through it, so there's one queue delay. In the Pegasus case, we use Condor glide-in, so again, there's one queue delay, then we get some resources, and then Condor glides the jobs into that resource pool that it has reserved. So again, there's just one queue delay. The tasks are different, I said. There are some gaps between tasks, which generally don't matter, although they look a little funny on the graph. Accuracy is pretty uncertain because all this stuff basically is running on a parallel file system, on this machine. And we've got our jobs, our 64 jobs in this case, that are accessing the parallel file system at the same time, and in some cases are looking at the same files at the same time. We've got other people's jobs that are also using the parallel file system. And so these are not repeatable experiments by any means on a production system. I believe that the numbers that were on the last two graphs are averages of 3 runs. But if I did it a different month, it would be probably somewhat different still. So the numbers aren't really important. The key thing is that we've got about the same amount of time here overall. Okay, so since we did this, and this finished about 2006, 2007 roughly, there have been additional work that's been done to look at cloud computing for Montage. I'm not actually sure if Montage was actually run on any real systems in this, or it was just an analysis. It wasn't clear to me when I read this. But there's been at least thought about how this should work, how Montage would run on clouds. And Montage has been used by a bunch of different people, including some people here, because it's a nice application and it's easy to get, and the data is easy to get, and it's easy to run. So it's been used to compare a bunch of different workflow systems at different times as well. So to summarize on the Montage piece, it's a custom astronomical image mosaicing service. So I didn't really mention the custom part, but that's because that workflow you could change around as you want. You could put in your own pieces. If you don't like the background correction or rectification that's being done, you can put in your own. You don't have to do that. You can do different pieces. It's public. There's an MPI version that has the best performance but requires a set of processors with a shared file system. There's the Pegasus Dagman grid version that has pretty close performance, has built-in fault tolerance, and can use multiple sets of processors, and can move files around between them. So I didn't mention, on the MPI version, right, if something fails, the MPI job fails. And the script itself probably fails if it's a pretty simple script, and you have to start again. The Dagman version has the idea of rescue DAGs, where it kind of keeps track of what's happened, and it can resubmit the rescue DAG afterwards, which would just do the pieces that need to be done afterwards. So the fault tolerance is quite a bit better and is more fine-grained and easier to recover. So overall, the grid version of this it's flexible and efficient, and it works reasonably well. And that's basically what we advertise that people should do. Although in practice, local usage is easier, and what actually happens at IPAC, where this is run as a service, is they have, I believe, a 64 processor system, and they run small jobs locally on their system because small jobs they can run with fixed time, with fixed response time, and give people back the answers. Larger jobs they send off to TeraGrid or somewhere else. They take longer, but people expect longer jobs to take longer, so that's okay. So it's nothing's quite as simple as it ever seems like it should be. But basically, Montage is an example of having this transition from parallel to grid for a problem, a workflow problem particularly. And this works reasonably well, and again, people use this now. Okay, so coming back to clouds. So what I think is the case is that we can look at clusters, at grids, and clouds, and try to look at some things about them. In general, in clusters and grids, you have queues that are important. In clouds, and here I guess I'm really talking about EC2 more than anything else as an example of a cloud. You don't really have queues. You have either success or failure in your request to get some resources. The resources on clusters and grids generally are thought of as being scarce, and on clouds they're generally thought of as being abundant. Whether or not that's true in the long run, again, is another interesting question. Right, in terms of coupling, we do tightly coupled things on clusters. We do loosely coupled things on grids and clouds. Clusters, generally, we don't really run dynamic applications. We run pretty statically mapped applications onto clusters. On grids, in theory, we could run dynamic applications, but we really don't in general, or at least most people don't. On clouds, it seems like new things are more dynamic, but old things that are being mapped probably are staying static or being ported. I guess the last piece of this is that the operating system and the tools, so in clusters and grids, we're looking at physically the physical system we're running on. In clouds, we're looking at a virtual system usually. Okay, and so as I was saying, I'm not sure that any of these things are really intrinsic, but this is, in general, what people in the US seem to think when you talk about clouds. And that's mainly because EC2 is the kind of the common thing that people think about for clouds, I believe. For private clouds, this could be different, and in Europe, this is definitely different in terms of these definitions, in my opinion, at this point. So it's interesting to look at some examples of what you can do if you try mixing things. All right, so we could take NAS parallel benchmarks that were developed for parallel systems like clusters, and we can try to run them on clouds like EC2. And so we can compare the performance of these 8 benchmarks on a machine at NCSA that's a cluster and on EC2 as a cloud system. And so that's the black and the blue bars, and the red dotted line is the performance degradation, percentage degradation over time on the axis on the right. So this one's about 200% degraded, about twice as long on the cloud than the grid. This one's about 10 times Right, this one's not too bad. So we can do this. Questions that come up are why do you have these performance issues? And a lot of it is because we've got virtual communication going on, or we've got communication that's being virtualized rather than going on the physical hardware. There's overhead there. There's overhead in I/O. There's not really I/O in these benchmarks in particular, but in some cases that's an issue. So this was done by Ed Walker about a year and a half ago. And then not too long after that, Ian Foster kind of did this interesting comparison where you take the idea that one of these things, the LU decomposition, has a runtime of 25 seconds on the cluster and 100 seconds on EC2. But you can say pretty much that on EC2, if you wait 5 minutes, your chances of finishing are going to be 100%. And if you look at Q prediction on the cluster, you have to get out actually quite far before you get up to a high percentage of chance of being done. Right, so even though the cluster is faster, in practice it may not be faster, and what we look at first may not be the right thing to look at overall. In addition to that, there are issues again about why these delays come in, why the cloud is slower on these examples than the cluster. So I just want to mention before I talk about that for a second, NSF has, yeah. I'm sorry. Yes. Is this really just sort of latency versus bandwidth? I don't think I'd call it latency versus bandwidth, but it's, well, so yeah, you're right. It's like
double the time of your benchmark, right? What's going to happen with these curves? Right? You're just going to shift that
yes.
line out by 2.
Right. It's not going to shift too much. It'll shift a bit as well. But
you'll get more bandwidth in the good system and lower latency in the cloud system.
Right. Right. Yeah. So if we were running things that took 2 days to run, then this wouldn't be in. Right. Then we wouldn't do this. So yes. So from that point of view, yes, you're right. Okay. So I just wanted to mention there are 3 different clouds that are in theory available from NSF at this point. For people to play around with free if you don't want to pay for Amazon or you don't want to use a private cloud. So there's the Clue system, there's an HP, Intel, Yahoo system, and then there's this new Windows Azure system. And the Yahoo one is the only one that you get the kind of the infrastructure as a service access to that you could do these experiments on. But I just wanted to mention that these are available freely under some kind of weird conditions at this point. Okay, so DOE is looking at some of these issues and again looking at why are the cloud applications slower? Do they need to be? What could we fix about this? So there's a couple of different things here. They're looking at the idea that we're looking at something in between a big supercomputer and a small cluster, but they're also looking at these other pieces about what's the software stack that works for science on a cloud versus for Amazon on the cloud. If you have situations like infrequent big runs or data-intensive computing, how do you actually do those things? And the system that they're building at this point is kind of interesting because it's basically it's a cluster interconnect, high-performance storage, so it looks like cluster storage. High bandwidth, wide area networking outside, so this looks like a cluster again, and middleware and scientific software that are similar again to what you would have on a cluster. And so the question that comes up is if you build something that really is a cluster, but you provide cloud interfaces, how does that change the way that you answer questions about what you run on a cloud versus what you run on a cluster or a grid? So I think that's an interesting question that hopefully in the next year or so will be answered from experiments that will happen on this system. There's a couple of other things going on in terms of MPI on clouds as well. There's something called Penguin on Demand, which is running what they call HPC as a service. And so this effectively is a virtualized scalable cluster on demand that looks like a cluster. And when you put jobs into this, it tries to group them in the way that actually maps them onto the same physical cluster. And they include support with HPC expertise. SGI has a product like this as well. that is, again, HPC as a service, that either could be software as a service, which is not particularly interesting unless you happen to run one of the applications that they're running, but it's also infrastructure as a service, so again, you can experiment with different systems on this. So given this kind of range of clouds that are coming available, what I and a few other people wanted to do was to use Montage and try to explore some of these questions about how do you do this mapping onto clouds, what are the important features of clouds. We also wanted to look at some issues that came up in building Montage, specifically that the development, it seemed like, was more complex than it should have been. Writing this MDAG code was not simple. There are some other ways that we could have done things about it. The fact that we've got a DAG that goes from abstract to concrete at one step means that we can't make runtime decisions based on data as we're running the workflow. So that's one of the things that we really would have liked to have been able to do. So as an example of that, we're running a job. We're using a couple of clusters, and we know that there's a high-speed network path between those clusters that's not being used currently. So that might change the way we map the job. So we might map it onto multiple clusters and make use of that network connection. On the other side, we have Montage that we'd want to use on clouds. We'd like to make runtime decisions based on resources as well. Sorry, kind of mixing these two things up, but the same idea. But also we want to control resources. So we might want to say that we're running this workflow in two stages. We know that in 30 minutes we're going to need a network connection between these two stages, so we'd like to reserve it now. All right, so how do we basically integrate resource information and data information into the DAG? So we started looking at these things. There was a paper in eScience last year in December that gave some initial results. And I'm just going to talk about a few of the things that we did that are very initial at this point. I also should mention I'm a member of a theme in the UK that's one of the eScience Institute themes, it's called Distributed Programming Abstractions. And so there's a team of 5 of us that have been looking at what are the abstractions that we should be using for programming, what have been used successfully in applications, in distributed applications today, what have been used in parallel applications but not in distributed applications, what are used in cloud applications, how do we put all those together into some kind of a mapping that makes sense that helps future application developers. And then the main question that we're looking at is basically if we assume that these are the objectives that we have for developing distributed applications, interoperability, distributed scale-out, extensibility, adaptivity, and simplicity, can we come up with some software that actually lets us do those things in general for applications? And what we're exploring at this point is a variety of frameworks, including Saga, which is the simple API for grid applications, and specifically we're using Montage to actually do this. So these two things kind of come together here. So I don't know, are people familiar with Saga at all? Is that concept? Yes? No? No? One? Okay. So this is one slide that didn't project very well that basically talks about what Saga does. So we have an application, we have an API layer that has abstractions that are exposed to the application, so files, jobs, remote procedure call, other things. The application writes to this API and it doesn't know what's underneath. It just knows the API. And so the idea is that this enables the application to be written in a way that it works on a variety of different middlewares. So the different abstractions then, say jobs as an example, has adapters that make it work on Globus or the OMI UK stack or G-Lite. And once you have the right adapters, then that actually then works with the different middlewares. And if you have the right middleware, then that gives you the right production infrastructure. So this is Condor Open Science Grid, Globus TerraGrid, and Cloud System. So in theory, by doing this, we can write applications that can run on a variety of different infrastructures without the application being aware of the infrastructure. And so that's what we're experimenting with. The specific thing that we've been doing, well, the specific thing that we wanted to do was we started off here in the Montage case where we've got a code that generates a DAG, it generates an abstract DAG. Pegasus takes that and generates a concrete DAG, and DAGman then runs that using Condor on some resources. We wanted to change this so that instead of using Condor, we could use a Saga tool that could then use Condor or EC2 underneath, so we could run part of the job on a standard cluster or grid and part of the job on a cloud. This is almost impossible to do. I don't know, whoever, the people that wrote DAGMAN wrote it very nicely and very efficiently for what they wanted to do it for. They wanted to do with it, but they didn't write it very extensively or very generally. So a grad student spent about 6 months trying to do this and then gave up. And basically rewrote the functionality of DAGMAN in something simpler to make this work. The other piece is that Pegasus, again, is a one step in general. It goes from an abstract DAG to a concrete DAG. We wanted the ability to go back and forth. So we wanted something that looked like Pegasus but could also read a concrete DAG, and we could work with it then. So if we had runtime information about a system, we could actually make use of that at that point. So we built something called DigiDAG, which is a very simple Pegasus-like workflow enactor. And I should say that in the case of both of these components, neither of these are intended to replace these components in a production setting. They're both really just used for experimenting and for trying to understand what we're doing here and how we would want to do things. And possibly we'd take lessons out of these and then try to give them back to the authors at some later point. So DigiDAG basically it's an API for programmatically expressing workflows, a parser for abstract or concrete workflow descriptions, an in-time workflow planner, and a workflow enactor that uses the Saga engine. And so it can take MDAG's output or Pegasus output, and we can, as I said, move back and forth between the abstract and the concrete DAG. And we're really just starting to work with this. So what we've done up to this point is we've run kind of a toy problem, a very, very small mosaic using DigiDAG, and then we've done a bunch of different submissions with that. Running this on a laptop, we can do local submission of the tasks using Fork. We can do local submissions of the tasks using SSH through Saga. So we're SSHing from the laptop into the laptop. It's not very exciting, but it does the functionality. We can do local submission using Condor. Again, the laptop is a Condor pool with 2 processors in this case. And then we can start combining these so that we can do 2 of these 3 or all 3 of these for different pieces of the workflow. And once this works, then we started using Queen Bee, which is a cluster in Louisiana, using the SSH connection. We started using EC2 using an Amazon Web Services connection inside Saga. We did both of these at the same time. Then we started mixing local and remote. And so at this point, we've demonstrated that all this functionality works, and we can use it to do more. But we haven't done more yet. So that's basically where we are right now. The goal here, in terms of what we're trying to do, again, is to understand distributed data-intensive scientific applications and how they use infrastructures. Trying to do this so that we can move back and forth between different infrastructures without the application writer being aware of it, but giving good performance. And so there's a bunch of different issues that fall out of this: coordination of the data and the computing, affinity, locality, understanding them and being able to specify them. As I was talking about before, runtime scheduling, including network scheduling, doing placements, fault tolerance. Effectively, the overall challenges here that go for any application, not for Montage, are basically to think about what the components are of the application that we're distributing, how the functionality is expressed, or what functionality is exposed, how the components are coupled, how we actually do the coordination, and a bunch of other things. Again, using Montage as an example to try to address these problems. Okay, so that's a lot of different things that have happened. Let me try to wrap up all this into a message. So in my opinion, static applications like we're using today in parallel don't have much to gain from the clouds that we have today. We can run them there, but it's not really a very useful thing to do. The emerging HPC as a service and new private clouds such as Magellan certainly could change this, and I kind of look forward to seeing how some of this happens in the next year or 2. There's also research in removing some of the VM overhead. There's pass-through communication and pass-through I/O that the VM folks are working on that also could help this situation. Overall, for a lot of the applications like the FTTD application that have been around for a while, in looking at the middleware and the infrastructure, we have to recognize that the application is probably not going to change very much after 20 years. It's pretty set. New applications will come out, but these existing applications, if we want to run them on different infrastructures, we have to look at changing the infrastructure to match what the application is expecting. There are other applications that can clearly gain from the clouds that we have today. Using platform as a service is simple for the applications that can be rewritten to do so. So as an example, the DAG-based applications should be able to run on Azure pretty easily. We haven't done that yet. That's something that we would like to do and improve. And the new applications can be the most flexible. If we start throwing out old assumptions and we don't start with a cluster model when we're thinking about a cloud application. And possibly something like Saga, and I'm not part of the Saga team, but I like the idea very much. Maybe an interesting way of trying to use grids and clouds together. And then finally, just to go back to this definition that I started with from the NIST definition and to highlight a piece of it. So I personally think the important thing at this point is that the cloud is an abstraction between the computing resource and the underlying technical architecture. When I or somebody else develops applications, we develop them for specific underlying architectures usually, whether they're abstract or not. And I think the big question is what an abstract architecture for clouds is that application users can think of in their mind when they're developing applications. And I don't have any idea what the answer to this is. It's not what it has been. It's something new. But I think that's an interesting research question. Finally, just to list, there's a bunch of different people that have been involved with a bunch of the different parts of that, so I just wanted to leave their names up when I finish and say thank you. Now you can tell me what I didn't tell you. Okay?
So can you explain the distinction between static and dynamic applications? Is it just a question of whether they're statically schedulable or?
So I don't think so. I think it's a question of what I guess there's probably multiple answers. So one is what's the abstraction of the architecture that's underneath? Right? Does the application assume that it gets some resources, it uses them the whole time until it's done, and then it gives them back? Or does it assume that the resources can come and go over time and try to take advantage of that? I think that's probably the biggest issue. But there's also the question of how the application is programmed in terms of a programming model. Right? So the MPI programming model is static. Well, I shouldn't say it's static by definition, but it's almost static it's static in regular use. In theory, it could be dynamic, but I don't know of anybody that actually does that. Whereas a workflow model is very dynamic because, well, at least in theory, it could be very dynamic because we could take advantage of more processors coming if we were still in the abstract space and map things to that at that time. So I think it's two different things. It's the underlying architecture and the programming model both.
But then that should be four choices, right? You have dynamic applications running in static architecture and so on and so forth.
Right. Well, yeah, I'm not sure that dynamic applications on the static architecture is a useful one, but the other three probably are. And I guess what I'm personally interested in is effectively is the two where we have the dynamic case in both. How do we do things there? And particularly, so it's interesting when I was first starting to work for Cray, which was when the T3D came out. I took a class on parallel programming because I was going to go from Cray to JPL, and I was going to sit with people for 3 years and help them write their programs in MPI and use these new parallel systems. And the person that was teaching this said that there's a kind of a thought process that has to happen where you go from a sequential mindset of your application to a parallel one. And that for most people that takes a few months. And at the time that seemed pretty reasonable. I don't think that's at all the case now. I think that people do this much more quickly now in hours or days at the most. But in terms of the static versus dynamic, I think we're still in the point where thinking dynamically takes a long time. And so I'd like to get to the point where the dynamic piece is implicit. And we write applications based on that. And they may run on static architectures, but they also can run on dynamic architectures.
So for people writing new applications, what are the learning materials that are the most efficient for them to come to grips with how to use these sorts of resources?
So in learning materials, I don't know. I think there's some interesting things that come together, I think, in fault tolerance on some of the exascale machines and some of the large machines that are coming. in some of the distributed systems. And so I think that those two kind of match together reasonably well, that if you can think of either one, you think of a kind of a planet-wide grid where you know resources are coming and going, or you think of a very large system where you know some resources are going to be failing at any given time, to at least have that model in mind as you're writing an application. But I honestly don't know of any good learning materials at this point. That's an interesting question. I mean, I guess using something like Planet Lab as a development platform or something like that, where you have kind of high levels of faults, would be one way of trying to do that, but I haven't actually done that. Okay. Well, thank you again. I'll make the slides available to okay.